Okay. Got that going. All right. Let's cover the new material today. I don't think that there's one new definition in this entire section. And I think everything we're proving today is pretty intuitive stuff. So.
Is that everything?
Almost. We have one little proof at the end that we'll need to do. Just proof with absolute values. But I think this is all pretty intuitive, so let's just get through it and then you have the rest of the day to do your homework. Or any questions that you have. So starting here, if f, I don't know why I did capital H and B, so it should be lowercase. If f from AB to R is integrable, we can take the integral of it. Some of the given information that we get when we know something's integrable is that we are guaranteed that there is an Archimedean-Riemann sequence on that interval for that function. And remember, an Archimedean-Riemann sequence is a sequence such that the gap goes to 0 in the limit. That make sense? So we're guaranteed that our approximations are going to get arbitrarily good. Our rectangles are always going to get arbitrarily small for calculating the area, so our approximations will always get arbitrarily good, is one way you can think about it. So we have f from AB to R is integrable, and we've got C is some point between A and B. What are we going to prove? We're going to prove that the integral from A to B is equal to the integral from A to C plus the integral from C to B. So in other words, you can split that integral in half and calculate it half that time, and you still get the same thing, which is obviously very intuitive for you when you think about integrals in terms of area. I can calculate the total area by first calculating this area, then this area, and just adding them together. Very intuitive. So,
is that a useful tool sometimes when you're integrating?
Yes, very useful. You could easily be going the other way as well. But yeah. Anyways, let's prove it. Let f be a function on AB such that f is integrable. What does that give us? That gives us that there exists a sequence of partitions, an Archimedean-Riemann sequence of partitions, such that the limit, all today, every time I do a limit like that, it's the limit as n goes to infinity. We just don't need to worry about other limits right now, so I'm just going to write that. So we're guaranteed that there exists an Archimedean sequence of partitions, such that the limit of the upper Darby sum minus the lower Darby sum is 0. You remember that? And we used the fact that this is true last time to prove that that means that we can do this. So the integral from A to B is equal to the limit of those upper Darby sums or the limit of the lower Darby sums. We could have used either one, it doesn't matter. Good so far? Remembering everything we did last week? Okay, so now what am I going to do? I'm going to take so this is a sequence of partitions. So it's a partition, and then find a partition, and then find a partition. That's kind of what it's doing, getting arbitrarily fine. I'm going to take the sequence of partitions, and to every one of those sequence of partitions, I'm going to add the point C in there. So if this partition didn't already have the point C, adding to the point C just makes the partition finer. It just broke it up into more pieces, right? And breaking up a partition into more pieces doesn't ruin anything. You remember the, what was it called? The refinement lemma? If we give ourselves a refinement of a partition, it only gives us a better approximation. It can't give us a worse approximation. So if this sequence of partitions is an Archimedean-Riemann sequence, the gap goes to 0. My adding a point isn't going to change the fact that the gap still goes to 0. Does it make it true in the sense that adding the point C to every one of these partitions doesn't change anything? We can now just say point C is in there. And you can do that for any point. You can add any point to the sequence of partitions as long as it's in there that you want. It doesn't change anything. Okay, so note that adding C to every Pn doesn't change anything. Reference the refinement lemma. Okay, so that makes sense. So what am I going to do? I'm going to take the sequence of partitions and I'm going to break it up into two halves now. I'm going to take the sequence, I'm going to take the partition from the point A to the point C, and then the partition from the point C to the point B. I'm splitting the partitions in half. That's what we're going to do here. So let Pn prime and Pn double prime be the partitions Pn induces on AC and CB. That was the terminology. I don't know if we used that terminology last time, but it's the terminology that your book uses. We take this partition, which is more than this interval, and the partition that this induces on this interval is like intersecting this set with this set. That's exactly what it is, actually. So it's just a set intersection, if you want to think about it that way. If you want to think about it splitting the partition exactly in half, with both partitions having the point C, that works too. In case we're missing this, let's just make it very clear. Here's A, here's B. I've got some partition on there. What am I doing? I'm saying we're going to add the point C here. And now I'm going to split this into two partitions. The partition of all the points from A to C, and then the partition of all the points from C to B. That's all I'm doing. So Pm prime is now going to be the partition on these points, and Pn double prime is going to be the partition on these points. Okay. Oops. All right. So now I know that the overall partition is an Archimedean-Riemann. I know that the overall sequence of partitions is an Archimedean-Riemann sequence of partitions. So its gap goes to 0. Notice that if I take just a piece of that partition, its gap still goes to 0. If the gap of the whole thing, if the biggest interval on the whole thing goes to 0, then the biggest interval on just this part for sure goes to 0. And the biggest interval on just this part for sure goes to 0. Okay. So that's how I know that this and this, when I look at their sequences, are still going to be Archimedean-Riemann sequence of partitions, and so we're still going to be able to take the integral on this and on this. Remember, it's integrable if and only if one of these sequences exists. Since I know that one of these sequences exists, I know it's integrable. So I know that, okay, so then the integral from A to B of f is the same thing as the limit of the upper Darby sums. I see how I'm doing this one now. So is the limit of the upper Darby sums. Now I'm splitting my limit of my upper Darby sums into on the first partition and on the second partition. So I'm calculating the rectangles over here first and then the rectangles over here using the upper limit, the upper Darby sums. So that should make perfect sense. Let's see, what do I do from here to here? Oh, I just split it up into two sums. The limit of a sum is the sum of the limits. That's all we're doing there. And then, since I know that this is still an Archimedean-Riemann sequence, then this is the integral from A to C, and similarly, this is the integral from C to B. And we're done. So nothing crazy new there. Very intuitive stuff. It might feel a little bit awkward working with these partitions at first, but I think once you have if you keep a picture in your head of what exactly they're doing, that helps guide you in the proof. All right, so no questions on that? Just on to the next one? Okay. Let's see. If f is a function from AB to R, and g is a function from AB to R, and they're integrable, and f of x is always less than or equal to g of x, then the integral of f is less than or equal to the integral of g. So I have two functions, f and g. If g is always greater than or equal to f, we expect the area under g to be greater than or equal to the area under f, is the intuitive way to say that. So it makes obvious sense to you that this should be true, and that's just mere proving it. So since f and g are integrable, then there exists some sequence of partitions such that the integral from AB to f is equal to the limit of the upper Darby sum with that sequence. And similarly, the integral from AB to g is equal to the limit of the upper Darby sums with that sequence. Just using the fact that they're integrable, right? Now, observe that for any partition P, then, the upper Darby sum, okay, I use some weird notation here. When I use y sub I, it's going to be a point in the interval x sub I minus 1 to x sub I. And it's going to be the point that maximizes the function value. So if I have, let's just draw one of these intervals. I should have explained it better, and I even had space to, so relying on words more than I should here. We're looking at a particular interval of this function. So here is x sub I minus 1, and here is x sub I, and the function goes on way further, right? And the function is defined, looks however it looks on that interval, so it looks something like that. Well, let's make it not be one of the endpoints. Let's make it look like this. So there's what the function looks like on that interval. I'm defining y sub I, so that y sub I is the point in that interval that that maximizes the function height. That's my y sub I. Okay. And I explained it better over here when I did a similar thing. But if you understand that's how I'm using my y sub I think that this will all make sense. Okay, so the upper Darboux sum on F with the partition P is equal to the sum of the max points times the interval length, sum it up. That's just a definition of the upper Darboux sum. You're used to seeing a big M sub I there. You'll see why I'm not using a big M sub I. So that's going to be now less than or equal to. Notice that this sum and this sum are the exact same thing, except for now I just replaced the F with G. So the y sub I was the point that maximized F, not necessarily maximizing G. But since F is less than or equal to G, I don't like what I did here. Because this isn't equal to the upper Darboux sum, but it's less than or equal to it, which still keeps everything true. Okay. So this is a point that maximizes F on that interval, and here is just a sum. We have numbers times distances. Over here we have those exact same distances, but all we did was replace F with G using the exact same point y sub I. We know that G is greater than or equal to F at every point. So going from here to here, all we did was make it bigger. Does that make sense? So G on this interval might look something like this. Notice now that G at y sub I happened to be its lowest point on that interval, but that doesn't matter, because G at y sub I is for sure greater than or equal to F at y sub I. So that's how this inequality is true. And since we're not guaranteed to get the max point there, if you were to replace it with the max point, you could have only made it bigger, which would give you the upper Darboux sum. Okay. So, then what do we have? Then the integral from F is equal to the limit of the upper Darboux sum is equal to the limit of that, which we know is less than or equal to the limit of that, which is equal to the integral from A to B of G. There's something weird there?
So why did we use y instead of just m?
Just so that I needed a way to capture, look, all I'm going to do is replace F with G to make it bigger.
Oh, and m that doesn't work with.
Yeah, I thought about using M sub Fi or something like that. I don't know.
Because big M is equal to f of y sub I, right?
Yes.
Okay.
Big M sub I for this function on that partition is the same thing as this. This is the same thing as big M sub I. But over here it's not necessarily the same thing. It's just the same point. Okay. That proof makes sense? No questions? Alright. Next one, a lemma. If f from AB to R and G from AB to R are bounded, notice we're not saying anything about integrals in this one. This is just going to show inequalities that are in general true for bounded functions. So if f from AB to R and G from AB to R are bounded, then for any partition P, the lower Darboux sum of f plus the lower Darboux sum of G is less than or equal to the lower Darboux sum of f plus G is less than or equal to the upper Darboux sum of f plus G is less than or equal to the upper Darboux sum of f plus the upper Darboux sum of G. These things don't have to be integrable, these functions don't have to be continuous, they just have to be bounded. That way we're not dealing with infinite values.
Is this supposed to make intuitive sense?
This one does not make as much intuitive sense, and I'll give you the function to think about to help you see why this one appeals to intuition, and then why this one appeals to intuition, and obviously this appeals to intuition already, right?
Yeah.
So I'm going to define two functions here. I'm going to say f of x is equal to 1 if x is rational, and then negative 1 if x is irrational. And I'm going to say that g of x is equal to 1 if x is irrational, and then negative 1 if x is rational. Right? Now, hopefully you see right out the door that f plus g of x is always 0. If it's a rational number, f of x spits out 1, g of x spits out negative 1, add them together, you got 0. If it's irrational, f of x spits out negative 1, g of x spits out 1, add them together, you get 0. So f of x plus g of x is always 0. Okay? So this one is always going to be 0, and this one's always going to be 0 with these two functions. This is just an example to show why these aren't equal signs, but they're less than or equal. That's all I'm getting real quick. But now, notice what is the lower Darboux sum of f if you do it on the interval 0, 1?
How can you take the integral of something that oscillates so much?
Not an integral. These are not integrable functions.
Okay.
We are just calculating lower and upper Darboux sums, and you can do that for any function, no matter what it looks like.
I see.
Right? We're just picking a partition, making rectangles, calculating the area of the rectangles. You can always do that. Doesn't matter what the function looks like, right? As long as it's bounded, so you're not trying to add infinities. Because, yeah, this function is a very crazy function. If you graph these things, what does it look like? Here's our x-axis. Here's our y-axis. If we graph this thing from 0 to 1, it basically looks like a solid line up here and a solid line down, not there, and a solid line down here. Because you plot all the rational points go up here, and the rationals are dense in R, so you're going to fill it up. And you plot all the irrational points down here for the first one, and then swap for the next one when you graph it. So, yeah, these are crazy functions. Anyways, so it makes sense that these two are always 0, but now let's look at the lower Darboux sum of f from 0 to 1. What's its lower Darboux sum?
1. Isn't it always 1?
No. Notice that for any small interval I pick in 0, 1, what is the minimum value the function reaches on that interval? Negative 1.
Okay.
So the lower Darboux sum, the height's always going to be negative 1. That's always going to be little m sub I. It's always going to be negative 1. And when you add up all the distances, you're going to get from 0 to 1, or 1. So the lower Darboux sum is going to be negative 1. So this is going to be negative 1. This is going to be negative 1. This is going to be 0. This is going to be 0. This is going to be positive 1. This is going to be positive 1. With this example. Now for integrable functions, if you take the limit, these are all going to be equal. But we're not talking about we're not talking about functions we can take the integral of. We're just talking about functions in general that all we know is are bounded.
Alright.
Does it make intuitive sense now how this thing's going to go?
A little bit more.
Okay, maybe leave this one up here in case we need to come back to it, and let's go through the proof real quick. Okay. Alright, let P be any partition of the closed interval A, B, because that's the interval the functions are defined on. And let big I sub little I be any interval of the partition. You remember what an interval of the partition is? The partition has n intervals. We're just picking one. And I'm going to show what we're going to do in one of those intervals, and we're going to do that in every interval. I'm going to do something similar to what I said down here, but now I'm going to be more explicit. So let P be any partition, and let big I sub little I be any interval of the partition. Then for any function h has nothing to do with these functions up here. For any function h from a, b to r, we're going to define n sub I of h to be the supremum, the max value that h achieves in that interval, and little n sub I of h to be the infimum of what h achieves in that interval. These are almost defined identical to the way that we use big M sub I and little m sub I already. It's just notation now where we pass in the function we're talking about. So when I do big M sub I of f, then I'm talking about the function f, and when I do big M sub I of g, I'm talking about the function g. So this is making very explicit the notation that we're going to use. But I think the notation would have made sense even if we didn't make this explicit, because you're probably already pretty used to it. But there it is, unequivocally, exactly how we're going to use these. And if I use this notation down here like I should have, then we would have replaced this f of y sub I with big M sub I of f. Make sense? Okay. So we've got that defined. Okay, now let's continue with the proof. Then f of x plus g of x is always less than or equal to the max point f attains plus the max point g attains on some interval. Maybe think about it this way first. Pick an interval, x of I minus 1 to x of I. Then for any point in there you pick, plug that point into f, plug that point into g, their sum is always going to be less than or equal to the max value that f achieves on that interval and that g achieves on that interval summed together. Does that make more sense? Okay. Alright, so notice what I have. I have f of x plus g of x is always less than or equal to this sum. So this sum is an upper bound for this sum on this interval. By definition of supremum, this is the least upper bound for this sum on this interval. This is unupper bound for this sum on this interval. This is the least upper bound for this sum on this interval. Therefore, this is less than or equal to this. You see that?
Aren't they equal?
They're going to be equal sometimes, they're going to not be equal other times. That's why it's more intuitive where they are equal for you, but over here was an example where they're not equal.
So when the function is continuous, they're equal.
We'll get to continuity in the next section.
Okay.
And the nice properties that continuous functions have with intervals. I think what it's going to be is if it's continuous and bounded, or continuous and defined on a closed interval. Both those should be the same thing. Anyways, we'll worry about that next week, or the week after. We have spring break next week, right? Has that been officially decided?
Yeah.
Good. Okay. So we're all good with this inequality, right? Least upper bound, unupper bound. So the least upper bound has to be less than or equal to any upper bound. We could have done similar thinking to show that the sum of two things that are lower bounds is less than or equal to the greatest lower bound. So this is going to be a lower bound for this. This is the greatest lower bound for this. Therefore, this is less than or equal to this. Greatest lower bound, a lower bound, greatest lower bound. Same way this was an upper bound, least upper bound. That make sense? It's almost identical thinking. It's just going to flip your inequalities because we're talking about infimum instead of supremum. Good? Okay. So now, just writing all these things out. Make sure it's very clear exactly what we're saying. So then, the sum of all the m sub i's of f times their intervals plus the m sub i's of g's times their intervals is going to be less than, notice that this is exactly what their lower Darboux sums are. Their lower Darboux sums are going to be less than or equal to when we combine them. Since I know that this plus this is less than or equal to this, then when I multiply by the same things, it's still true. So I knew that this number plus this number was less than or equal to this number. Now I just times them all by the exact same intervals.
And then,
And I'm summing them up.
but now we're talking about all the partition intervals, right? Not just the one we were talking about before.
Yeah, we've just used a particular interval to define our notation for a particular interval. Now we're adding up across all the intervals. Since we know it's true for any interval, we know it's true for every interval. And so we're summing up for all the intervals. So that's how I'm getting that this is less than or equal to this. That is just using this inequality right here. This inequality gives me this, the sum of these two is less than or equal to this. By definition, we already knew from quarterback when we first started that this one is less than or equal to this one, right? That's just a lower Darby sum is less than or equal to an upper Darby sum. And then using this inequality here, we know that this sum is less than or equal to these two sums. That make sense? Okay, now just replace those with the notation that you already know we can use. I just wrote them out as sums explicitly so you can see where we're using these pieces. But now, rewriting the exact same thing. The lower Darby sum of f with p plus the lower Darby sum of g with p is less than or equal to the lower Darby sum of f plus g with p is less than or equal to the upper Darby sum of f plus g with p is less than or equal to the upper Darby sum of f plus the upper Darby sum of g. See how those are identical? Okay. This is just more consumable now. Oh no, that's it. That's what we were trying to prove. Thought we had one more step. Nope, that's what we were after. This big long inequality. I think your book breaks them up into some separate ones and does just one piece at a time and then the next piece, but this made more sense to me. Okay, next proof. Oh, unless we have any questions on that.
So, we talk about continuity next week. We'll look at when. Well, what I'm wondering is, are we going to find out in what cases they're equal rather than just less than equal to? So we obviously it seems like the lower Darby sum of f plus the lower Darby sum of g should
F
be
and G
equal.
are both integrable on their intervals, then let's see. Oh, that's exactly what we're going to prove here. The integral of f plus g is equal to the integral of f plus g when they're both integrable.
Okay.
So that's exactly the next proof. And we're going to use this inequality, and you can probably already see how we're going to use it now, which is why the proof feels small. All right, so let's start it. If f from ab to r and g from ab to r are integrable, then the integral from a to b of f plus g is equal to the integral from a to b of f plus the integral of a to b of g. So since f and g are integrable, then there must exist some sequence of partitions such that the lemma of the upper Darby sums of f is equal to its integral, which is also equal to the lemma of its lower Darby sums, and the lemma of the upper Darby sums of g is equal to its integral is equal to the lemma of its lower Darby sums. Good with that? Anything weird? Okay. So then, oh, I just flat out did it without even referencing it. Okay. Probably should have put one more line in there, but we'll point up here as we do this. So then, the limit of this plus the limit of this is less or equal to the limit of this, right? Since I know this plus this is less than or equal to this, well, the limit of this is the integral from a to b of f plus the integral from a to b of g is less than or equal to the integral from a to b of f plus g. So this is taking the limit of their lower Darby sums. So I should have done one more step here. I should have used this with limits in there, and then rewritten it as this one more time. We're going to do the exact same thing for this. That's just using this half of the equality. The limit of this is less than or equal to the limit of this plus the limit of this. So the integral of f plus g is less than or equal to the integral of f plus the integral of g. Obviously, if they're less than or equal to each other, they're equal to each other. Now that make sense?
Yeah. Just to clarify though, we do know that if f is integrable and g is, then their sum is?
We could have put another line in there saying, note that since Pn is Archimedes-Riemann sequence on AB, then we can also use it for this function. Since we could use it for this, we can use it for this. We can use the exact same partition. Because its gap is going to go to 0. The gap goes to 0, the gap goes to 0.
I guess, but how
we can find an Archimedean-Riemann sequence on AB for that function.
We can for f and g, but how do we know for f plus g?
You could take the refinement if you want, but already whatever partition works for this is also going to be a partition that works for this, is also going to be a partition that works for this. Because it's a sequence of partitions defined on the closed interval such that its gap goes to 0. And so if the gap goes to 0 for this one, it also does for this one, it also does for this one. Because they're all defined on the exact same interval.
Right.
So I could use a regular partition for all 3 of these, and it works. I don't need to find a separate partition for the various integrals. I just need one where the gap goes to 0 on that interval, and it works.
I guess we'd be using that in the fact that if f is continuous and g is continuous, then f plus g is continuous.
Nope, nothing about continuity here. The only thing that we need to clarify is that f plus g is still bounded since f and g are bounded. Integrability implies bounded, and then I can only add up my upper and lower Darby sums if it's bounded. Otherwise, I might be adding up an infinite area.
All right.
So 2 things that we're playing fast and loose with: the fact that f plus g is still bounded, and the fact that whatever partition, sequence of partitions works for these also works for these. Also works for this.
Okay.
That makes sense? Good? Any other questions on that? Okay. So, we showed that the sum, the integral of the sum is the sum of the integrals. Now I'm going to show that an integral times a constant is the same thing as a constant, or the integral of a constant times the function. I'll point it out and say it because I'm saying it wrong. So if f from a b to r is integrable, and if alpha is any real number, then the integral from a to b of alpha times f is equal to alpha times the integral from a to b of f. You can factor constants out of integrals, in other words. Make sense?
How? That makes sense.
Okay. So, since f is integrable, then there must be the sequence of partitions such that the lemma of the upper Darby sum is equal to the integral is equal to the lemma of the lower Darby sums. Observe that Pn is also an Archimedean sequence for alpha times f on AB. So we know that that integral exists. If that sequence of partitions makes the gap go to 0 for f defined on AB, then it's going to make the gap go to 0 for alpha times f defined on AB.
So, does an Archimedean sequence just work for every function?
Defined on the same interval.
Find the same interval. So any function you choose, that one sequence can do it for all.
Yep. As long as the function's still bounded. So we probably need to say also observe that since f is bounded, alpha times f is bounded. Because if this can be encased in a number big M, then this whole thing can be encased in the absolute value of alpha times big M. Right? So that's one thing that we didn't explicitly state, but I think it's pretty clear. So now we need to handle 2 cases. We need to handle a case where alpha is greater than or equal to 0, and a case where alpha is less than 0, because it's going to flip our upper Darby sums into lower Darby sums and vice versa when it's negative. So we'll start at the positive case because that one's pretty straightforward. If alpha is greater than or equal to 0, then the upper Darby sum of alpha times f on P, notice that this is just a big sum where we have alpha times the height times the interval over and over again. So we can factor the alpha out of that sum. This is just a sum where alpha is multiplied by every term. We can factor alphas out of sums because it's just constant. So that line makes sense? Then obviously in the limit we can still do that. So then the integral from a to b of alpha times f is the limit of the upper Darby sum of alpha times that. We can factor alpha out of the sum, so pull alpha out of the sum. And then we also know that you can pull constants out of limits, which is what we do here. And then compute the limit, and we're done. Anything weird there? Okay, similar thing. If alpha is less than 0, then the upper Darby sum of alpha times f on P is equal to alpha times the lower Darby sum of f with P. This might not be so obvious until you think about it for a second. Notice that if we're talking about the upper Darby sum, we're talking about the highest point that alpha times f spits out. Well, if alpha is negative, then the highest point this spits out is the smallest value this spits out, because we're multiplying it by negative. So overall, the highest value the product spits out is when f is at its lowest point. Think about f as a function that's both positive and negative. This is a negative number. We want to multiply it by a negative number to get positive. And the more negative we can make that number, the more positive their product is going to be. Does that make sense? So, in other words, since we're doing the upper Darboux sum of alpha times f, that's the same thing as alpha times the lower Darboux sum of f. We were really using the lowest values of f to get the highest overall values. No? I thought that one would be more clear. Maybe one picture will make it really, really clear. I'm going to start out with the function f. And we'll make it do something like that. Now I'm going to multiply the function f by -1. What does that do? That makes it look like this. Notice now that the lower f was, the higher alpha sub f was. So this function right here is f of x. This function right here is alpha times f of x. I can't remember which one I called it first, but we'll call this one f, and this one alpha times f, where alpha is some negative number. We're picking -1 to keep the picture simple. So notice that high points here correspond to low points here, and low points here correspond to high points here. So if I was using, so if I'm doing the, lost where I was, right here. If I'm doing the upper Darboux sum on alpha times f, so alpha times f, we're talking about its highest points, that is going to correspond to alpha times the lowest point on f of x.
Oh, okay.
Is that better?
Yeah.
Okay. And you'll have homework problems where you prove this. Did I do that wrong? Oh, that's very, very equal to down here. That'll be a homework problem for you, so hopefully you'll get more comfortable with that. Writing this out all the way explicitly. So you'll have to reference actual sums to do this proof. Anyways, if alpha is less than 0, then the upper Darboux sum of alpha times f on p is equal to alpha times the lower Darboux sum of f of p. Okay, so now then the integral of alpha times f is equal to the lemma of the upper Darboux sum, so that's perfectly fine. Factor out the alpha, turns the upper Darboux sum into a lower Darboux sum. Factor the alpha out of the limit, and we're still doing the limit of the lower Darboux sums. But the limit of the upper Darboux sums and the limit of the lower Darboux sums are the exact same thing, namely the integral from a to b of f. Anything right there? Okay. And then our very last proof is just proving that the integral of an absolute value is equal to the absolute value of the integral. I think. Actually, I should make one more note of something that the author does. So my doing this and my doing this is not what the author does. The author does this. Prove that the integral of alpha times f plus beta times g is equal to the integral is equal to alpha times the integral of f plus beta times the integral of g. So he does all that proof in one go. Notice now that the way that I proved it, we can do this over two proofs now. I proved that if you have an integral of a sum, that's the same thing as a sum of the integrals, so that would take us to the integral of alpha times f plus the integral of beta times g. And then here I proved that you can pull the alpha and the beta out, which gets you to here. So I did first prove that the integral of the sum is the sum of the integrals. And then I did a proof that the integral of a constant times the function is a constant times the integral of the function. The book does a proof the integral of a constant times f plus a constant times g is equal to the constant times the integral of f plus a constant times the integral of g. Which you can see how using my way still does that. It just breaks it down don't like how they're trying to do it all in one big old go. And they do it a bit different from me, so if you read how they do their proof, then you can get some extra insight into all that. And there's less of a chance that there's a problem with their thinking than there's with mine, so maybe I made a mistake, and with them you'll get it all nice and clean. Okay, so our last proof. This one on top. If f from AB to R and G, and the absolute value of f from AB to R are equal, then the absolute value of the integral from a to b of f, maybe I'll use Leibniz notation like they do, fx dx, just to reintroduce the notation. The absolute value of that is less than or equal to the integral from a to b of the absolute value of f of x dx. Okay, it makes sense what those two things are saying. The absolute value of the overall integral is less than or equal to the absolute value of the function, and then integrating that. That makes sense? And does the inequality sign in there make sense? Let's draw one real quick to make it very obvious. Let's say that I have a function that's down here like this and then up here like this. So its overall integral, if we go from, we'll call this point -1 to the point 1, is going to be 0. That makes sense? But notice if we take the absolute value of the function first, then that brings this line up here. And now when we take its integral, we're going to get 2. So that's an example of why these definitely aren't necessarily equal. Make sense? Okay. So let's see if we can prove it. Let's think back to our absolute values. So showing that the absolute value of this is less than or equal to this is the same thing that's showing that the value inside of it is sandwiched between the negative of this and the positive of this. So maybe start there. Observe that negative f of x absolute value is always less than or equal to f of x is always less than or equal to the absolute value of f of x. That one pretty intuitively clear? Two. Then, how do we want to write this? What was this function defined on AB? The integral from AB of negative absolute value of f of x. We'll put the dx in there. Dx is going to be less than or equal to the integral from a to b of f of x dx is going to be less than or equal to the integral from a to b of the absolute value of f of x dx. That one makes sense? Notice that integrals you can get in terms of sums. So this would be the height for all our sums. and then to convert them to upper or lower W sums, we're just going to multiply them all by the exact same intervals and sum them up. So those being true, hopefully I don't need to rewrite this as a sum and then write this. Hopefully you can start thinking about these as sums, as like infinite sums.
Didn't we prove that in your second theorem?
Oh, I don't know.
That if one function is always less than or equal to another.
Oh, there we go. Yep, good call. So yeah, we don't even need to think about that way. So yep, I know this is less than or equal to this, so this is less than or equal to this. I know this is less than or equal to this, so this is less than or equal to this. Good? Okay. Okay, so now, I mean, notice that you can think about that negative as a -1 and pull it out, so you can pull negatives outside of this if you want. So I don't know the best way to help you see this. Maybe I'll just write it like this and we'll be good. So then negative, so pulling the negative out of this, negative the integral from a to b. I don't want to rewrite the whole thing with just pulling out that negative. Notice that if I pull that negative out, then we now have it of this form. And so now we can do the inverse of what we know, which means that the absolute value of this is less than or equal to the thing we have over here. So I have the negative of this. Look at this thing, I have its negative right here. So I have this value sandwiched between this and its negative value. So then, maybe if I would have just written this, then we can think about backwards and that would help more. Then the integral from a to b of f of x dx is less than or equal to the integral from a to b of the absolute value of f of x dx. So if you were to think about how we would undo this one step, that's exactly what this is. The absolute value of this, less than or equal to this, is the same thing as the value inside my absolute value is sandwiched between this and its negative, which is exactly what we have here. Does that make sense? The same way that the absolute value of a is less than or equal to b is the exact same thing as negative b is less than or equal to a is less than or equal to b. Here's my b. Here's my b. Here's my negative b. Here's my a. Good? Okay, that's the last proof.
That was fast.
Yeah, no new definitions, no completely new ideas, just proving some things about integrals that are actually pretty intuitive. Just working with sums. Good?
Yeah. Are we going to go over at some point the integrals of absolute value functions in more detail? Because it seems like if, I'm just trying to think of it this way, like if you can't have the derivative of an absolute value function at certain points, then how does that look when you try and take the integral?
First off, you can take the integral of the absolute value function just fine.
Right. And it seems like
But
we'll be able to.
remember, where was it? The first one. Just split the integral where you're at your 0, and then replace all your absolute values with negative x's. So you can take your absolute value function, split it into 2, and then work with it exactly the way you know and love. Where absolute value of x becomes just x if you do from 0 to b, and your absolute value of x over here becomes negative x if you do from a to 0.
Is it not very? It's probably easier. Is it easier to do that than it is to just try to take the integral?
Depends on the problem. I mean, I'm sure there's problems where that's a useful substitution. I'm sure there's other ones where it's like that's overkill.